finished yesterday with an example showing with a video application how our network characteristics can impact on the quality of that video. The example showed that we could stream video across a network. Increasing the delay had little impact. We increased the delay from about less than 1 millisecond up to 500 milliseconds, half a second, and still the video streams okay. Increasing the jitter has an impact, so we'll explain why that's the case. Jitter is the variance of the delay between the packets. And the first one was we increased the packet loss. That is, we introduced packet loss into the network. And that can have an impact as well. The amount of impact it has depends upon the network, depends upon the content that we're watching or sending. What was the data rate of us sending the video across the network? That is, what data rate was required to send the video. Let's have a quick look. The file itself was, what's that, 4 megabytes. So it was only a small video over, what, 30 seconds or so, 4 megabytes. In the past, I captured that stream using Wireshark and TCP dump. So not yesterday, but before when I tested, I captured using TCP dump all the packets sent and opened that in Wireshark, and it tells us in Wireshark, so these are all the packets that were sent across the network in that streaming of video. They're just UDP packets. We'll see shortly in this lecture that it's in fact using RTP as a protocol to send the packets. So the server was .3, the client was .2, and the server is sending many UDP packets containing that video across the network. And a summary of the statistics tells us on average across that capture the megabits per second, 0.787, so 780 kilobits per second for streaming that video across the network. So in terms of what do we require to get a good quality video stream across a network, in this example around less than 1 megabit per second is sufficient. If we want higher resolution video, then this is going to be higher. So data rate was okay because we had a 100 megabit per second link. We only need less than 1 megabit per second, so we were fine there. Delay was okay, jitter was not so good, and packet loss was not so good on the impact of our video. So let's explain first how jitter and delay are handled for multimedia applications. Here's a simple example. So what happened in our example yesterday is that the source, the server, takes the video, puts it into packets. As we saw in the capture, it sends UDP packets across the network, usually at a fixed rate or at a regular interval. And then when the receiver receives each packet, it takes the contents and uses it to create the video to display on the screen. So if we receive packets at a regular rate, then we can play back the video at a regular rate, and we'll get smooth playback. If we get jitter, variance between the delay of the packets, we'll get problems in the playback of the video. Let's explain that with a simple example. This diagram shows a sender and just 4 packets that are being sent by the sender to the receiver across some network. The source is sending a packet every 40 milliseconds in this case. So create a packet, transmit, 40 milliseconds later, send the next packet. Think very simply that the packets are containing some part of the video, say a frame in the video. Remember, a video is just images, frames, which are played back at a certain rate. Just imagine, it's not the case because in video we compress and we use different codecs, but imagine each packet contains a frame of video. So the source is sending packets at a regular interval, every 40 milliseconds. They're sent across the network. The network has a delay of 50 milliseconds. And the jitter is 0 in this case, which means that every packet experiences a delay of 50 milliseconds. There's no variance in the delay. So packet 1 is sent at time 0, therefore it will be received at time 50 relative to when it was sent. And packet 2 was sent 40 milliseconds later, will be received at time 90, which is 40 milliseconds after packet 1 is received. And packet 3 and 4, there's an error somewhere there. What's the error? It's Thursday morning, time to wake up. What's the error in that diagram? What are the numbers which are wrong? 80. Should be 0, 40, 80, 120, 160. So you can fix that. That is, originally I had 5 packets, but I couldn't fit them in the diagram and I removed the wrong one. That is, it should be 0, 40, 80, 120, 160. And on the receiver side, 50, 90, 130, 170. I've used the wrong numbers. So in this case, 50 millisecond delay, no jitter. What happens at the receiver? The receiver wants to play back the video and play it back so it looks like it's a smooth playback. The receiver cannot start playing back the video until time 50. So if we contact the server and press play, then it takes 50 milliseconds for the first packet to arrive. So after we press play, there's this short delay of 50 milliseconds. And then when the first packet arrives, the receiver application takes the content from that packet and plays back on the screen. Let's say shows a frame on the screen. And then 40 milliseconds later, it shows the next piece of content, the next frame, for example. And then 40 milliseconds later, the next part of the video and the next part. And if we keep going with all the packets, then the source is sending packets every 40 milliseconds, and the frame is receiving packets every 40 milliseconds and can play back the content every 40 milliseconds. And we get a smooth playback of the video or the multimedia content. Because why are we sending every 40 milliseconds? Because that's what the source thinks is necessary to deliver this audio or video across the network for sufficient quality. In this, every 40 milliseconds means one packet, actually 25 packets per second. The rate is 25 packets per second. Why did I choose that in this example? Just as a very simple case, let's assume that every packet contains a frame of video. A typical frame rate for video is 25 frames per second. So we want to play back the video at 25 frames per second. So it gets smooth. From our eyes, it looks like there's motion. So in this simple example, let's say the source takes a frame, sends it in a packet. When the next frame is ready to be played, it sends that in packet 2, and the next frame in packet 3 and packet 4 and so on. So we're sending one frame per packet. The receiver receives one frame per packet, one frame per 40 milliseconds, and to get smooth playback, it needs to play back at a rate of 25 frames per second. And it does. It's successful in this case. That is, the receiver can play back the frames, frame 1, 40 milliseconds later, frame 2, frame 3, frame 4, and so on. So there'll be smooth playback in this case, because we'll be playing the frames at the rate at which they were generated, 25 frames per second. There'll be a small delay between when the source starts sending and the playback starts at the receiver. Imagine you press play, it takes 50 milliseconds for your screen to start playing the video. After that, the playback is smooth. That's what we want. If the delay was not 50 milliseconds, but like in our example yesterday, 500 milliseconds, but still no jitter, then it would be the same. We'd get smooth playback, but we would get a longer delay at the start. Yeah? My example of saying one packet contains one frame is not a real example. It does not happen in practice. Yes, one packet can contain more than one frame, and in fact, normal video is compressed using a particular codec. We don't have the raw frames to send. We have some representation of multiple frames in the data. So it's not that simple. So in practice, we don't have to, and we normally would not send the packets at the same rate as the frames. But just for simplicity in this example, let's assume we do. In practice, because you compress, multiple frames may be, the information representing multiple frames may be contained in one packet, in fact. So this is okay in terms of playback. A small delay at the start, other than that, smooth playback at the receiver. Let's introduce jitter. Let's say there's some variable delay between each the packets experience. Sender sends at the same rate every 40 milliseconds, because in our simple example, the video is generating frames, 25 frames per second, every 40 milliseconds, a new frame. We send that new frame in a packet. And the receiver should receive the packet, play the frame, show the frame on the screen. Here I've introduced some delay variation. And let's write the numbers down so we get it right this time. The source and the receiver again, there's this error because I've copied the same diagram. It should be 0, 40, 80, 120. The first packet has a delay of 50 milliseconds. So we receive it at time 50. The second packet has a delay of 40 milliseconds. There's some jitter, that is variance between the delay of the packets. So if we transmit at time 40, we receive the second packet at time 80. The third packet has a delay of 60 milliseconds. It's not transmitted at time 120, that's where the mistake is, it's transmitted at 80. With a delay of 60 milliseconds, it would be received at time 140. And the fourth packet has a delay of 50 milliseconds, transmit at time 120, receive at 170. So you can fix this slide, the errors in the numbers there. So the delay 50, 40, 60, 50. So the delay is going up and down over this small period. The average delay is still 50. The average of these four numbers is still 50 milliseconds. So the average delay across our network is 50 milliseconds, but we have some variation. Now, what does the receiver do? When it receives a packet, it takes the frame inside that packet and shows it on the screen. So at time 50, it plays back. So this is the time when the packet is received. This is the time when that frame is played back on the screen. At time 50, the first frame is shown on the screen. When we receive the next packet, we immediately play back. So at time 80, Note the time between those frames being played back is 30 milliseconds. We were generating frames at a rate every 40 milliseconds, or an interval between frames of 40 milliseconds. Because 25 frames per second. We should play back at that rate. That's what we need to get smooth playback. Here, we do not play back at that rate. Because we receive packets with varying delay, the next one we play back when we receive the packet. The delay is 60. And the next one at 170, the delay is 30. So imagine, it's not easy to visualize, but imagine, okay, one frame is shown on the screen, the first frame. A short time later, the next frame is shown. And then there's a large delay between the display of the second frame and the third frame. We'd expect a delay of 40 milliseconds, but it's in fact 60 milliseconds. Now, whether your eyes will notice that extra 20 millisecond delay, probably not. But over a long period of time, if there's many frames being displayed, you can think that a large delay between displaying of frames looks like some freezing of the video. It stops. We'd expect frames to be played back at a regular rate every 40 milliseconds to get this smooth motion. If they're not played back at that rate, if they're delayed longer than 40 milliseconds, then you can imagine that it will be shown as the video freezes for some point of time and then starts playing again. Playing back at a shorter time, maybe it skips over. So the variation in the time at which we play back those frames results in these artifacts in the playback from what the user sees of the video. And that's bad. This is a simple example because it only considers 4 packets. In reality, there'll be thousands of packets, and the jitter have to be significant such that the receiver cannot play back at a reasonable quality. We saw yesterday with a jitter of, what do we set it to, 200 milliseconds in our simple network. We could see the problems with the playback of the video. It wasn't the video freezing and starting again. Because of the way the codec works, it means that some content could not be displayed. We saw this pixelation in some parts of the video. That was because of the jitter. Because some frames, the video didn't have the content to play it back at the right time. So it couldn't play back everything. So that's a problem. How do we fix it? We can buffer frames or buffer packets. So in this case, average delay is still 50. Jitter is present. Results in a problem for our receiver, playback at the receiver. We can overcome that, at least partially, using a buffer at the receiver. We transmit the same as before, receive with the same delay, so the source, the receiver. Instead of playing back the video as soon as we receive the packet, save it in a buffer for some period of time and play it back slightly later, with the intention of playing back at the same rate at which it was generated. That is, playing back a frame every 40 milliseconds. That's what we need to get smooth playback. In this case, we receive packets at varying intervals. We want to play back the frames, the content, at a regular interval. We can do that by buffering some of those packets, as shown here. Here we're going to buffer for 20 milliseconds. We'll come back to why I chose 20 shortly. That is, when we receive the first packet, we don't play it back immediately. We play it back after a delay or a buffering of 20 milliseconds. So we receive it at time 50, we will play back at time 70. in this example. And from now on, what we want to do is play back the next packet, the next piece of content, every 40 milliseconds to get this smooth playback. So let's see if it works. It should work in this example, the way I've set it up. We receive packet 2 at time 80. We want to play back at time, what time? What time do we want to play back the second frame? First frame played at time 70. When do we want to play back the second frame? (110). We're generating every 40 milliseconds. We want to play back every 40 milliseconds to get this smooth playback. So this is the desired playback time. So in the first packet we receive, we buffer it. We do not play back immediately. We save it in some memory and then play back 20 milliseconds later at time 70. The second one we play back, we receive it at time 80. We play back at time 110 such that the difference here is 40. The third one is received at time 140. When do we play back? The third one? 150. Simple. 40 milliseconds after the second one. That is, when we receive the packet at time 140, we save it in a buffer for 10 milliseconds and then play back. And 190 for the next one. This is the time when we play back the content, and playing back at a regular rate means we get this smooth playback again. It's the same rate at which the content was generated. And that's what we need for smooth playback. We've achieved that by introducing some buffering at the start. That is, do not immediately play back, save it in some memory, in this case for 20 milliseconds, in this case for 30, here 10, here 20. The initial one was the most important. So by buffering, we can achieve smooth playback. The problem, the disadvantage, is that now, from when the first frame was sent, 0, until the playback starts, is larger. It's now 70 milliseconds. In the first case, with no jitter, the delay to start the playback was 50 milliseconds. When we introduce jitter, the delay until we start the playback is 50 milliseconds, but without buffering, it won't be a smooth playback. Using buffering, we can smooth the playback, but we've introduced an extra delay from when we start at 0 until we start the playback of now it's a total of 70 milliseconds. So we increase the delay from when you press start until when the video starts playing on your computer.
But if the jitter is so high, buffering still will have freeze frame, right?
So the question is, what if the variance is larger? What happens? Which points to the question, why 20? Why did I choose 20? How did I choose 20? In this example, if I knew that the jitter is going to be less than some value, then that is, it's not going to be greater than, in this case, our jitter is plus or minus 10, that it's 50 plus or minus 10 from 40, the packet delay is from 40 up to 60, then I can select the initial playback buffering time such that if the jitter does not go above 40, above 60 and below 40, then I can design this initial time such that we'll still be able to smoothly play back those frames. But if the jitter is larger, I choose 20 here, and it turned out that that last packet had a delay of 80 milliseconds, transmitted at time 120, took 80 milliseconds to get there, received at time 200, the scheduled time to play back should be 190. According to our initial buffering time of 20 milliseconds, we start the first packet at 70, then the next one at 110, that's okay. The third packet at 150, because we have this interval of 40 milliseconds. We'd like to play back the fourth packet at time 190. But we don't receive it until time 200, so we cannot play it back. So we'd have to play back at 200. Again, we have this variation in the playback. And we have this variation in the smoothness of the video. So if the jitter, so importantly we need to select this number appropriately, the initial delay. The larger the initial delay here, the larger jitter we can cope with. If we delayed this to 100 instead of 20, then we start at time 150, 190, 230 and 270. We should have received the packets by that time. But the problem of making this larger is that there's a larger delay between when we start, that is press play on your video, until when it's played back on your screen. So there's the trade-off. We introduce a buffer which should be large enough to cope with the jitter in the network, but small enough such that it doesn't delay the start of our video too long. Knowing what that value is, well, it needs to be predicted. You're not always accurate. So you watch a YouTube video, if the network quality is not so good, then you press play. It takes a few seconds to start playing the video, because in fact the server is streaming you packets already. You press play, the server is sending you packets, but your client is not playing the video until it's received enough packets. It buffers those packets or that video. And then it starts playing, so that even if there's some period of time where the network slows down and they cannot send you packets fast enough, you still have enough in the buffer to continue playing the video. So the longer the initial buffer, the more that we can cope with large delays between packets, large jitter. But the longer the initial buffer, the longer you have to wait until the video starts playing. That's the trade-off there. This is a very simple example looking at individual packets. In practice, it's more complex. But the point, if we want to overcome jitter, we can use buffering. We need to predict what is the initial value to buffer such that the user is happy. They will not have to wait long enough before it starts. It adds some extra complexity in the receiver, but not too hard. And of course, we need some memory for buffering. But again, in most computers, that's not a problem. So most video and audio streaming applications will use buffering to compensate with jitter. Any questions on how that works? The concepts.
About the live streaming,
Mm-hmm.
if the buffer is initial delay or buffer is too high, so it may not live.
Yeah, when we said yesterday we can talk about streaming of stored data or live data. With live, we'd like a very small delay from when the content is generated at the source to when it's viewed or heard by you. So with live streaming, normally our buffer size will be less than we can use for stored streaming. With stored streaming, say watching a YouTube video, I may be happy to wait for 5 seconds before it starts playing, so long as I get smooth playback. With live streaming, I may not want to wait 5 seconds from when the content is generated at the server, the live action happens, until when it's played on my computer. I would like it to be live, that is, I see as it happens. So we cannot have large buffers when we have live streaming.
Sometimes I watch the online TV and the frame playing and it's suddenly skipped to another frame.
So again, if the buffer is not large enough at the start, then if we do have a large delay sometime later, then the application has to cope with that somehow. And one way is to stop or freeze the video at some point and try to build up the buffer again. So if we don't receive packets because the network link is very poor for 10 seconds, then we have nothing in the buffer to play. So we basically freeze the video and then hopefully start receiving packets so we can start playback again and maybe skip several seconds of video and move on to the next part. So yes, you'll see that happen. And it's all related to what's happening here. Any other questions on jitter and playback buffers? So just note that my numbers for packets 3 and 4 are wrong in those 3 slides. I need to fix them. They were wrong last year. Okay, so a summary of what we just said about buffering can deal with jitter. Now we'll look briefly at 3 different examples. We'll look at voice over IP, we'll look at streaming of audio and video, and then look at IPTV. I think we know this from our study of quality of service, that the internet doesn't provide any built-in quality of service. It's a best effort service. We send the packets and we hope they get there. There's no priority mechanisms given between the packets. Voice is not given priority against web browsing without these extra mechanisms that like diff-serve and int-serve. And most networks don't have them. Or the internet as a whole does not have quality of service built in. Yet, without these quality of service mechanisms, and even without multicast, because most networks do not support multicast yet, we still have multimedia applications successfully used on the internet. Let's look at voice over IP. Making a voice call across the internet. There's just different terminology that you may hear. Voice over the internet protocol, VoIP, voice over IP. You may hear IP telephony, IP phones, and so on. All similar. There's some subtle differences in some cases. As an example, Skype is voice over IP software. Some network operators provide a voice over IP service. Say in Japan, you can, instead of paying for a landline phone, you just use your home phone is just a voice over IP service. Although it may not be across it may be across a separate network, not the normal internet access. So the network operator may build their network to support voice over IP. The main point here is that you may hear different terms. We'll talk about voice over IP. Voice over IP is reasonably simple. We take our voice, analog, we use a codec, convert it into bits, and we send those bits across the network from the source to destination. And how do we send them? Well, a common protocol to send them is RTP, Real-Time Transport Protocol. It's a protocol built for sending audio and video across the internet over an IP network. And it's used in a number of voice over IP applications. It was used in our streaming yesterday, the streaming of the video. In the Wireshark capture, although it doesn't show RTP, it was in fact RTP was used. If you recall yesterday when I started the client and even the application, there was one option there, RTP. It was specifying the protocol used to send the packets. So let's look at how RTP works. RTP your application, your voice application generates bits representing your voice. So you take from your microphone the analog input, converts that into bits using a codec, and then those bits are sent to RTP, the protocol, which puts them into a packet, and then RTP uses UDP and IP to send that packet and that voice across the internet. We do not use TCP. The problem with using TCP in a number of multimedia applications is that TCP works well for data transfer, but when we want fast transfer, real time, then TCP has some delays which can be significant. Remember, with TCP we send a packet, and we send some packets, and before we can send more we have to wait for an ACK. That introduces some delay. So, and if we lose a packet, we need to retransmit with TCP. There's some delay between sending packets. We want to be able to send the packets with constant delay, with small and constant delay. TCP is not so good for that. So it's common to use UDP. RTP allows us to put voice and video data inside some packet, include some identifying information, and send it as a UDP packet. Sometimes we'll consider RTP as a transport protocol, although it operates on top of UDP. Let's draw a stack. At the bottom, the physical layer and the data link layer, whatever they are, Ethernet, wireless LAN, anything, IP. Then let's consider this the transport layer. We use UDP and on top of that RTP, then our application. Our user generates the content. The application, for a voice application, implements some codec that takes the input signal and creates bits, a stream of bits. Those bits are the data that is put inside the RTP packets, and the RTP packets are sent in UDP datagrams using IP and our data link and physical layer, and sent across the network to the receiver, which looks the same as this. The receiver receives the IP packets, UDP, RTP, sends the bits to the application, the codec converts those bits back to analog output and plays it on the speaker at the receiver. So in terms of the data flow, that's our stack for voice over IP, and similar for other audio and video applications, streaming applications especially. So what does RTP do? It doesn't do much. It's a very simple protocol. It allows carrying any type of media, voice and video, so it doesn't specify which codec to use. You can carry voice information, video information, whatever you like. It includes a sequence number, so that when the receiver receives the packets, the RTP packets, it knows the order in which to play them back. If something arrives out of order, packet 1, then packet 3, then packet 2, having the sequence number allows us to reorder them or discard one that has arrived out of order. So it has a sequence number and some timestamp, again useful for the playback. We stamp the time from when it's sent, 0, 40, 80, 120. Therefore, the receiver, it knows when to play it back based on the sending time and the difference between the timestamps. It doesn't do anything complex like retransmissions, no priority mechanisms. It doesn't guarantee that the packet will arrive on time. It just sends the packet. So it's very simple. The idea is to be very simple, have very few overheads, so it can be very fast, as opposed to TCP that can be introduce delays. There's the packet format. The idea is to keep the packet small, again, small overheads. There's the data, which contains the digital voice, and the header, which is normally 12 bytes. There you can add some options. Some version, the version of the protocol being used, a sequence number, a timestamp, and let's look at the other values. Payload type indicates what's the content inside. Is it voice using what particular codec? Sequence number used to identify each packet. Let's say the first packet we choose a random number, the next packet add 1, and so on for the sequence number. If we have optional fields, we set the value of the X bit to 1. P bit is set if there's no padding after the payload. Sometimes we want to make the packets fixed size and we pad them out. So if we use padding or not is what the P bit indicates. M bit is used if the application uses some markers, some indicator in the content to say where we are. But that would be application specific, so it may not be used in a voice application. Payload type, this field here, indicates what's the content. What came from the application? And in particular, what codec? So there's a number to indicate different codecs and the options for those codecs. So if you're using PCM voice, the basic voice codec, the number will be 0. Using GSM codec for voice, the number will be 3. Using MPEG audio, the number is 14, and so on. There's video and audio codecs that are supported there. So the receiver knows what the content is in this packet, what the data is. Timestamp indicates when the data was sampled. And the last set are about indicating who's the source of this content. We'll come back to them, or we'll explain them, because we can in fact use translation and mixing and mix multiple sources into one stream using RTP. Translation is we can convert the content from one type to another. A source sends PCM high quality voice. We have some intermediate device that converts that into a lower quality voice, say for using a GSM codec. So that's translation. Translate the content from one format into another. That's a rather simple concept. We have our source. Let's say for simplicity we're streaming audio, streaming voice using RTP. Source generates some voice, it's sent across some network, and the source doesn't know about where the destination is. They know the address. They use PCM to encode that voice, which generates at 64 kilobits per second. So high quality for voice coding, the normal quality. So the RTP packets, the payload type would be 0 in this case. It's encoded using PCM, the data. The destination is here. This intermediate device, which is going to do the translation, knows that the destination is on a wireless network. Say a mobile phone. So it's a base station, for example. This is a wired network. Sending at 64 kilobits per second across this link, across this network is okay. The network supports that speed. But this device knows that I need to send RTP audio to some destination, but that destination is a mobile phone. Let's translate the content to use a different codec. Use, say, the GSM codec to reduce the data rate required to send, but also reduce the quality. That's the downside. So this device takes the RTP packets and translates the content from one codec to another. What is it, 13 kilobits or 14 kilobits per second. So takes RTP packets and generates new RTP packets where the content now is, so 0 was for PCM, the payload type. And in the output from the translator is the number 3 for GSM. So basically decodes what's received and encodes again using a different codec. So that's the concept of translation. So if this receiver only supports the GSM codec, then translation is needed, because if the source sends using the PCM codec, if the destination doesn't support the PCM codec, they cannot receive the data. They cannot decode it. So the translator, this special device, converts the content between two different codecs. So that's supported in RTP by using the payload type. And that's the only field we need. So that's one feature that's supported by RTP. You can simply translate along the way. It doesn't have to be audio, it could be video that's translated. Again, streaming from some server, high quality video, your mobile device only supports a certain number of codecs, not supported by the one that's originally streamed. The translating device converts into a codec that your receiving device can support. Of course, the translator has to be fast. Otherwise, it introduces a delay. And if we've got if it introduces a delay, we either need some buffering, or it may in fact introduce jitter. But that's a different issue. Yep.
This is as if I use Skype to call to mobile phone.
If you use Skype to call to a mobile phone, Skype doesn't use RTP, but let's assume it does. What does it do? Yes, similar. When you call a mobile phone with Skype, you actually connect to, well, no. What's the difference there? Skype or some voice over IP software client calling to some mobile phone, let's say calling to the normal mobile phone, not calling to a Skype application on the mobile phone, but not calling to just the normal mobile phone. The normal mobile phone is our antenna, base station. Here's our network of our, so here's our mobile phone, our base station, and our telephone network here. This mobile phone network connects to the PSTN, the public switch telephone network. It's a separate network from the internet, remember. Normally when we make calls on the mobile phone and home phones, we're within this public switch telephone network, separate from the internet. So there's some gateway device that connects from our internet, so our computer application is connected to the internet, sends to some gateway device that does this, that can do this translation, yes, and do other things as well. But the difference is that This is not the internet here. This is the public telephone network. PSTN, the public switch telephone network. So when you connect a voice over IP application to a traditional telephone, there's some special gateway device that does the translation and may do other things like charging and so on, making sure someone pays for that call. And over here, we're not using the standard internet protocols. We're not using RTP. We're just using a connection-oriented phone call. We set up a connection from the gateway to the phone. Essentially set up a phone call, a traditional phone call from the gateway to the phone, and as we receive data, we send it across that connection. With RTP, we're focusing just on using the internet all the way. But similar process, you need to translate. Another feature that RTP supports is mixing, taking the content from multiple sources, combining them into one stream. For example, a teleconference. We'll just focus in one direction. Let's say it's a teleconference between four entities, 4 users. 3 of them are on the one network. Let's say 3 are within SIT, and 1 is remote, somewhere else. And these 3, let's say there are 3 lecturers sitting in their offices, not in the same office, in separate offices, just sitting at their computers. And they're all participating in the teleconference. So what RTP allows is to combine the content from multiple sources, in this case from sources A, B and C. When A, B and C generate data, let's say computer A starts talking, then they use RTP to send the packets, and there's this special device in the middle that performs mixing. It combines the packets which are coming from A, B and C and combines it into one RTP stream. It mixes the different audio or video sources into one stream. And to do that, there are these extra fields. Some fields to identify who is the source. The number of sources contributing to the stream. So what we have here is, okay, the source is A, the source of this packet is B, the source of here is C, and the mixer takes the content from all of them, combines them into one stream or one RTP packet, and sets the fields appropriately to indicate how many streams it's combined into one, sends that onto D, and D can separate out into streams. Or D can play back and know that it's coming from 3 different sources. That's the idea. It works okay because normally, say in a teleconference, of those 3 users, A, B and C, normally there's just one talking at one time. So even though all 3 may be generating packets, the data from B and C, while user A is talking, may be close to silence, some background noise. So it's still sending packets, but the data or the audio is not so important. So we can mix them into one, saving space, not having to send 3 packets across the network, and D can play back the combination of them. Take an audio editor, take 3 different inputs, combine them together and send them as one output, play them back as one output. So that's using mixing in RTP. And RTP doesn't specify how to mix, it specifies just in the headers that you can indicate whether mixing's performed and who the sources are. That is, who's the original source and contributing sources. That is, A, B and C are the contributors. Mixing combined with multicast can give significant performance improvement. If we have many users, then mixing can save on space because we send one copy of the packet for multiple users, and similar for multicasts. If we have multicast in the network with many users, we don't have to send so many packets. So that's the basics of RTP. Your voice over IP application generates bits representing your voice, puts them inside an RTP packet which sends them as a UDP packet across the network. No retransmissions, no flow or error congestion control, just sends them. Includes these header values to identify the source, some timestamp and sequence number so we can play back correctly at the receiver, but that's it. So quite simple. If a packet is lost, it doesn't do anything about it. Because often we care more about getting a packet there within a short amount of time than having to deal with packet errors. We can tolerate some packet losses in many applications, but we cannot tolerate variance of delay. A related protocol is called RTP Control Protocol, RTCP. That's for controlling the session, for sending information about the quality being received from the destination and the sender, so some reports from the sender and reports from the receiver. For example, the receiver, when they receive packets, can send back some report saying, this is the quality that I'm receiving at. And maybe the sender will do something about that and to improve the quality or to reduce the sending rate to deliver better quality at lower performance requirements. So RTCP, if you see the acronym, refers to controlling the stream, not sending data but controlling the stream. Some exchange between the source and destination about the quality and so on. We will not say any more about that. So with voice over IP, we need to send the data. We use a codec. The data is sent using RTP. The other aspect of voice over IP is signaling, setting up the call. With a traditional telephone network, we have what's called signaling, where you pick up your phone, you dial in some number, the person you want to call, and then the telephone network sends some signals to the destination. The destination phone rings. When the user picks up that phone at the destination, it sends some signals back to your phone indicating that they've picked up. And then you start sending data. So before you send data, you perform some signaling. Traditional telephone networks have what's called the signaling system number 7, SS7. In the internet, we need a separate signaling system. How do we make a call or set up a call? That's what signaling performs in the internet. Two main signaling protocols in the internet, SIP and H323. SIP, the Session Initiation Protocol, and H323 has both separate signaling protocols. Perhaps the main one in use today is SIP, and we're going to concentrate on that. How is SIP used to set up a phone call? Once we set up the phone call, we use RTP to send the data, to send the audio. SIP is the session initiation protocol. It's used for setting up voice calls, but not just voice calls, also other multimedia application sessions. It can be used to set up video calls. It can be used to set up instant messaging sessions. So it's used not just for voice and video. There's a concept, there's the caller and the callee. The caller is calling the callee. So what SIP does is allows the caller to notify the callee that they want to call them, and allows the participants to negotiate and agree upon codecs. That is, make sure they're using the same codec so that when they send data, the receiver can decode, and to end calls, to finish the call. With voice over IP, we use IP addresses to identify entities that are the caller and the callee. We can do things in SIP like change the codec during a call. We can do things like conferencing, invite new participants into a call, have multiple people talking at the same time, a teleconference. Call transfer, call holding, and many of the normal things you expect in a telephone network can be supported by SIP. SIP is an application level protocol. It runs on top of UDP in most cases. The stack we drew here is for data transfer. When we're sending the audio, we use this stack. How am I going to draw it? Maybe you can visualize it like this. Where SIP is used for control of the session. Our voice over IP application uses SIP to make a call, which runs on top of UDP and IP. Once the call is established, we use RTP to send the data across that call. So we have two different protocols in use here. We would normally consider SIP an application level protocol. Even better maybe to draw it. It gets complex in that we cut across layers. It's part of the application layer. Whereas often you consider RTP part of the transport layer. Note that we see with layering, we've spoken always about 5 layers. In real life, it's not that easy. In real life, there are protocols that go across multiple layers and communicate between multiple layers. So SIP is an application level protocol, uses UDP in most cases, uses port 5060, and it sends text-based messages, similar to HTTP. Remember with HTTP, you send a GET request where the message contains the text GET followed by the URL or the path. Similar, SIP sends messages. They're not binary, they just contain some string with some meaning that the receiver can understand. We'll see some examples. Addresses are similar to email addresses. SIP : username @ domain. So that is a SIP address, for an example. So if you want to call someone using SIP, you need to know their SIP address. You enter that address in the application, and the session initiation protocol sets up a session between you and that destination. SIP doesn't say how to transfer the data. To transfer data after we set up the call with SIP, we can use RTP, but we can use other things. It doesn't specify how to do that. So they're separate, but common is to use them together. SIP to set up the call, RTP to send the data. But there are other options. We're not going to go through how SIP, all the different message types are structured and how it works in detail. We'll just go through this simple example to show how to set up a call. Here we have Alice, the person making the call, wants to call Bob. So they have their computers running. The IP addresses are shown for Alice and Bob's computers. Bob is running some voice over IP application. It just sits there running in the background. He's not talking yet. It's listening on some port number. So think of it as a server. So Bob's voice over IP application is sitting there running, listening on port 5060. Alice, when she wants to make a call, starts her voice over IP application and selects Bob's address to call Bob. So Bob at some domain. In this case, it's Bob at some IP address. If Alice knows his IP address, normally you would not. You'd have a domain name. And Alice's voice over IP application sends a SIP message to Bob. And the basic structure is it's an invite message. So the first word is invite, and then who we want to invite, who we want to call. Contains some information that is used to set up the data transfer. Here it contains the IP address of Alice. It contains something about the content for this session that we're about to establish. It's an audio session that we want to establish. We want to use RTP to transfer the data. And we want to use the codec identified by the number 0. If you go back to the slide on RTP, the payload field, the number 0 indicates the PCM codec. The number 3, GSM, and different numbers indicate different codecs. That's the payload field, or the audio-video payload, AVP, 0. So Alice wants to use Alice wants to receive content encoded using codec 0, PCM. And the other thing here is the port number that Alice wants to receive that data on, 38060. So we use port 5060 to set up the SIP call, but to receive the data, we use different ports. So for the data that Alice wants to receive, she wants to listen on port 38060, and she wants to receive PCM encoded voice, indicated by codec 0. Sends the invite to Bob's voice over IP application. When Bob's application receives it, it starts ringing or shows a message on the computer. When Bob answers, his voice over IP application sends back a response saying, OK, I will accept this call. You see it's using a similar format, similar structure as HTTP. Send back some status code and some status response, 200 OK. Include Bob's IP address that he's going to use for the data transfer. Note that for setting up the call and for the data transfer, we can use different IP addresses in theory. So we could have said that Alice wants to establish a call to Bob, but once we set up the call, we don't want to receive on this IP address, we want to receive on a different IP address. That's possible. Bob indicates what he wants to receive. He wants to receive audio using port 48753 and using the codec number 3, which is GSM codec. So Bob wants to receive using the GSM codec. Sends also to port 5060, that is the voice over IP application, and a final acknowledgement saying everything's received OK. So that's the session has been established. We've established the voice call. After that, they start talking. And that's what this shows. We start sending voice, but it's encoded using when Bob talks and it sends to Alice, the voice is encoded using PCM codec. And the name of that is called micro law. That's just the normal PCM codec. Because that was indicated by what Alice will accept, codec 0. When Alice talks, her voice is encoded using the GSM codec, because that was indicated by Bob as what he wants to receive. Codec number 3 turns out to be GSM. So they're using different codecs in the different directions. That's acceptable. Alice receives on port 38060, Bob receives on port 48753. And they just keep talking, and there's a way using SIP to end the call as well. So that's the very basics of SIP. There are many more options, but we just want to introduce that we can use it to set up a voice call. Who has used voice over IP software? Have you? Have you used voice over IP software? Yes. What software?
Skype.
Okay, Skype is the most common one. Skype doesn't use SIP or RTP. The Skype software uses its own proprietary protocol for setting up a call, and its own codec normally, although it can use different codecs, and its own protocol for sending data. So Skype, perhaps the most popular voice over IP software, does not use standard IP protocols. It uses IP, but it does not use RTP or SIP, which means it's difficult to connect, or difficult, in some cases impossible, to use some other software to call someone on Skype. Use another voice over IP software to call someone's Skype's number or address. You cannot. You need some gateway that will translate from that other software into Skype and make a call, which is complex. What about Google? Although I don't know if it operates in Thailand, I haven't used it. They have a voice, their own voice application. So Google has their own voice application that does use SIP and RTP for voice calls. Even I think the voice chat in Gmail uses SIP, and so in Gmail, you can chat, and in some cases you can do a voice chat. You can do a voice call. So I think that does use SIP and RTP for the transfer. Similar, MSN, Microsoft, they use, what do they use? They use their own protocol for voice transfer. So SIP and RTP is one combination. There are other proprietary ones that different companies use. Many of the international phone services you pay, you want to call someone overseas, you get a cheap price. Many of those phone services use SIP and RTP. That is, they use voice over IP. They no longer use the traditional public switch telephone network for international calls. They use the internet, and usually using common protocols. The benefit of using SIP and RTP is that you don't have to use the same application as the other one. So long as your application supports these protocols, you can use whichever application you choose. So you can potentially call someone on the Google network so long as their client uses the same protocols as your client. There's some extra complexity about how do we deal with addresses and names. That is, often we want to use a domain name, not an IP address. So we need to map that domain name to an IP address. We make a SIP call. So we will not go through in detail. There are ways to have proxies using SIP. If a user moves, they have their address, which is based at SIT, the domain name Steve at SIT, but if I'm not at SIT, I'm somewhere else, and someone tries to call me using SIP, where is the call directed to? Well, normally it would be directed to SIT's network, but if I'm not there, I'm visiting somewhere else. SIP has some built-in mechanisms using proxies and registrars to handle the redirection of calls to the destination. But we will not go through that in detail. The main thing is SIP is about setting up the call. Once it's set up, we use some other method to transfer the data direct, usually RTP for data transfer. SIP is built not just for voice, but also used for video and data calls, data transfer, voice calls, video calls, data sessions, especially instant messaging. Some instant messaging clients use SIP and can do so to set up a connection between the two people who want to send instant messages. Many IP phones, so now many ISPs offer a service where you can use the internet connection for voice access. You don't have to pay an extra fee to use the telephone network. You just use your home telephone line is a SIP phone. It's a phone that uses the internet. So many what's called IP phones will support SIP, RTP and RCTP for control of the data session. They may be implemented in software, a soft phone you just install on your computer, or standalone phones that you buy a phone and you plug into it an Ethernet cable and it uses SIP and RTP to make voice calls. It's different than the traditional phone. Or you can buy adapters for old style phones. Note that Skype uses its own protocol. So that's all about voice over IP. Yeah?
Do there any encryption mechanism in the RTP?
Yes, there's an option for RTP to do encryption. So not in the standard RTP, there's some extensions of RTP to do encryption. So you can encrypt the data. So your application could encrypt the data. That's the basic approach. So your application takes the analog input, converts it to bits, and then can encrypt those bits and put them into an RTP packet. So the application can deal with that. RTP can do other things, or actually more it's the codec to do encryption, compression, and so on to improve the performance. RTP just carries the data. It really doesn't care what it is, but you can specify the payload type. How are your voice over IP applications? Are you running one? Skype. Hmm? Viper. What does it use? Find out. There's your homework. See if you can call someone else using a different system. So many of Skype and other free services, they make money from people using their service. And one way to keep people to use their service is to use proprietary protocols, so you cannot communicate with someone else on a different service. The idea of SIP and RTP is that anyone that supports that protocol can communicate with anyone else. That's about voice over IP. Let's quickly, and I think we'll finish it today, is streaming stored audio and video. That is, we have some audio or video on a server, we want to stream it to a client. Rather simple. Examples: internet radio, YouTube. Content stored on a streaming server or multiple streaming servers. User requests the content, and there are different ways for that to happen. and then the content is sent from the server to the client. We saw that yesterday where I sent content from my server to the client, and that used RTP to send the content. RTP on top of UDP. You don't have to use RTP. If you look at VLC, the program I used yesterday was VLC. It's a media player, but it's also a media server. So I ran VLC on both computers. One was acting as a server, streaming the content to the client. And VLC supports different protocols for streaming data. I chose RTP yesterday. It supports streaming over HTTP and other protocols as well. So you can choose. So the idea for streaming is that we have content on some server. The user requests the content, say using a web browser. The user visits the website of the server and requests the content, or a media player, like I did yesterday using VLC. The request may be direct to a streaming server or to a separate web server. Let's see some examples of this. Here's an example where we have a server. It's a web server which has audio files. So I create a simple web server. I put on there the audio or the video files. These examples have audio. It can be replaced with video. Say the IT web server, and I put on there some video files. The client uses HTTP to send a request for a meta file, a file that describes that audio or video. The server sends back the meta file. The web browser, when it receives that meta file, interprets what it's describing and potentially asks your media player. Sometimes the web browser has a built-in media player, or it can ask an external media player to contact the server and stream the content. So some examples of the meta files, or the extensions: PLS, ASX, Smile, RAM, and there are others. So this, our server, say if we're doing video streaming, has the video files on it, and it also has the meta files, video. The meta file is just a small file that describes the content. Its location, the type, the owner, for example, usually a text file. And on the client, using the web browser, you send a request for the meta file. You send a request for you click on a link, which is a request for that meta file. That file is sent back. Your web browser sees the extension and understands what that extension refers to, and based on the content, potentially opens another application on your computer, a standalone media player, sending the content of that meta file to the media player. So you have a web browser, and let's say you also have a separate media player. Of course, now some browsers can have a built-in media player, a standalone media player. The meta file is sent there, video. The media player looks at the content of that meta file, which includes the location of the content, the format and so on, how it's encoded, and then sends a request to the server based upon the location to start the streaming. in this case using HTTP. So send a request for the video file. And then the server starts streaming the video to the media player. So that's a typical approach of using web-based access to stored streaming. Whether or not the media player is standalone or part of the web browser, still the same approach. Request some descriptor of the audio or video, and then tell the server to start streaming the audio or video. A small extension of that is if we have the streaming server separate from the web server. We have a web server which has just the description files, and usually they're the same formats. It's called here a presentation description file, but it's the same thing as with our meta file before. It's describing the content, and we have a separate server. So this is the web server, and somewhere else on the internet we have our streaming server. Which has the content. Send a request for the descriptor file. Media player looks in the content and sends a request for the video. And it starts streaming to the media player. So this is very similar to the previous approach, except we separate the web server that takes the requests from the streaming server which sends the content. And in the previous case, in this example, we use HTTP for both the request and the streaming. In this case, we use HTTP for the request only, request response. The streaming, we can use any protocol. For example, RTP. It's not needed. We could use HTTP, but we could use something else. So long as your media player and the streaming server support that data transfer protocol, we can stream using that approach. HTTP can be inefficient for streaming sometimes. It uses TCP. That's a problem. Other than that, very similar. I thought I had one more. Okay, that's the main ones. What about a flash player? How does that work? Many videos you watch on websites, the player embedded in your web browser uses Flash, a Flash player. How does that work? That's essentially your media player. Flash, that Flash application embedded in your website is, from the perspective of these two approaches, is your media player. So again, you send a request using a web browser to some URL. It sends back some descriptor of the content, which is a Flash file or a Flash descriptor. The Flash application on your computer starts. It's embedded in your web browser. And that Flash application, which is the media player, requests the content. And it's using HTTP, in most cases Flash. And the server starts streaming to the Flash player. So the most examples you see, the media player is Flash or some other media player in the embedded in the website. One other protocol that may come up is called RTSP, Real-Time Streaming Protocol, used for controlling playback. It's a way to send messages to start, pause, fast forward and so on, different controls, and for describing streams. And that's very, very quick coverage of how to stream audio or video using usually stored data, a stored audio or video, and also the same could be applied for live audio or video using the internet. The normal mode for access is you use a web browser or use HTTP, but the streaming can be done via HTTP or some separate protocol. It doesn't have to be HTTP. And the web server and streaming server can be separate. They can be in different locations. Next week we'll talk about IPTV and talk about the requirements for our network to support. Well, TV, it's still video, but when we talk about IPTV, we normally mean video at a quality which is the same as what you watch on your TV. That is, imagine if you have a digital TV and you receive digital TV at home, then you want to get that same quality on a large screen but across the internet. And normally, separate infrastructure is needed to support IPTV. That is, you don't necessarily use the same network that you get internet access. You may use a separate network. So we'll go through that next week.